Hi everybody, welcome to lecture number 9 for Physics 151. This lecture is a continuation of lecture 8 where we talk all about the mathematical tools of vectors. In lecture 8, it was mostly an introduction to vectors and magnitude and direction versus components. Today we're going to talk about some of the basic arithmetic functions you can perform with vectors. Namely, you can multiply them by scalars and you can add and subtract them from each other. We will not, in this course, in Physics 151 or 152, use dot products or cross products of vectors. So some of you may already be familiar with those, and that's great. And those do show up in physics formulas, but we won't use them in this course sequence. We're going to refer to the same sections of the chapter 1 that we used for the previous lecture. And of course, I'll be doing example problems from tutorial number 9. However, before we jump into the second half of vectors, I have 2 slides of review questions for you. So uh, please press pause now and try and answer these questions. Then I'll reveal the answers. Okay. All right, I'm going to reveal the answers now. I hope that these are the answers that you got. Just quickly to review, um, components of vectors can be positive or negative, but the magnitude of a vector is only ever written as a positive quantity. That's our convention. If you ever do get a negative value for a magnitude, perhaps either you just took the square root and didn't take only the positive value, or if you think that a vector should have a negative magnitude, maybe you should change the magnitude to positive and turn the direction of the vector around. So reverse the direction. For trig directions, remember, if you add or subtract 360 degrees, you wind up with the exact same direction. So 345 minus 360 gives you negative 15. Negative 15 degrees and 345 degrees are exactly the same direction on the unit circle. The same is true if we used radians. If you add or subtract 2 pi radians, you wind up in the same direction. Okay. The answers to 6 and 7, I'll leave to you. Here's one more review situation. Suppose that you're given this velocity vector right here, and notice how this is written in component notation. Okay, please pause the lecture and try and answer these parts A through E without using a calculator. No real calculation is necessary to answer these questions. So pause now. Okay, I'm going to reveal the answers now. I hope that these are the answers that you got. And just quickly, these first few questions are asking what are the two components, x and y components of the vector v naught, and what is the magnitude of vector v naught? Remember, that's what this is. This is the magnitude. If it's just the name in italics without boldface and without a vector hat. So looking at this component notation, we can see anything that's multiplied by I hat or multiplied onto I hat is the x component. So the x component is negative 3.5 meters per second. It's that whole thing. Notice when there is 0 multiplied by j hat, then we don't even write the j hat term at all. And the same is true for the k hat term. So what that means is the y component must be 0. It's not even written. The magnitude is going to be the x component squared plus the y component squared, square root, kind of like a Pythagorean theorem. So that is just 3.5 meters per second. Again, always positive by convention. So this negative value here is not, we would never write a magnitude as a negative quantity. You can also tell that one just by inspection. This is a vector that points in the negative I hat direction, so that's the negative x direction. And it has the length of this vector must be only the x component because there is no y component and no z component. So therefore the length of this vector is 3.5 meters per second in the negative x direction. So just by inspection, you can tell that the magnitude has to be 3.5 meters per second. Also, because it's pointed in the negative x direction, what's the trig direction and the compass bearing? The trig direction of negative x direction is 180 degrees, okay? Or to the left, as we normally would draw the axes. And then if we define positive x to be east and positive y to be north, and what's that compass bearing? Well, to the left would be a compass bearing of due west or 270 degrees. So it's from north measured through east all the way around. Okay, that's our quick review of last lecture's content. Let's move on to the topics for today, which, so we have a lot to cover in today's lecture. First, we're going to start off with scalar multiplication. So what do we mean by this? Scalar multiplication refers to taking a vector that's known and I'm going to call that vector A for now. And we want to multiply it by some sort of a scalar quantity. Now, there are a lot of formulas in physics where this shows up. And that scalar quantity could have units. So it could maybe have units of mass, or 1 over time, or 1 over mass, or time, or any other scalar quantity, okay? Energy, for example. And as a result, when we're done with that, you're going to have a new vector quantity. So we have a vector times a scalar, which gives us a new vector quantity. Now, if the scalar that we're multiplying by does have units, then what that's going to do is it's going to turn the new vector into a different physical quantity, different type of physical quantity than the old vector. For example, if the old vector had units of meters and we multiply by 1 over seconds, then our new vector is going to have units of meters per second, or distance over time. So in other words, we could have taken displacement vector multiplied by 1 over time and wound up with a velocity vector. So it's very possible. On the other hand, if the scalar that we're multiplying by has no units, maybe it's perfectly 1/10 or perfectly 2 pi or just some other just pure number, right? It doesn't have to be a pure rational number. It just could be a decimal. But if it has no units on it at all, if it's dimensionless, then of course A and B will have the same units as each other, and they will be the same type of vector. So if A is a velocity, we multiply it by 1/2 or 1/10, then B will also be a velocity. Okay, how do we do it? Well, there's sort of two approaches on this slide. The first approach is if you know the magnitude and direction of vector A. If you already know magnitude and direction instead of components, which is down in the bottom half, if you know the magnitude and direction, then here's the approach. To get the magnitude of the new vector B, multiply the magnitude of A by the absolute value of your scalar. Okay, so we're just basically taking the scalar, and if it has a minus sign, strip it off. Otherwise, leave it alone. Then what is the direction of the new vector? Well, if the scalar you're multiplying by was positive, then the new vector B has the same exact direction as the old vector A. Okay, so in other words, multiplying by a positive scalar does not rotate the vector at all. On the other hand, if the scalar you're multiplying by was negative, then the new vector is going to be exactly reversed from the old vector. You could either add 180 degrees or you could subtract 180 degrees. I didn't bother to write that here. Either way, whatever is more convenient, adding or subtracting 180 degrees from the direction of vector A will flip the direction of vector A, and vector B will now be in the flip direction. That's again, if the scalar itself has a negative sign on it. And then you're done, and that's it. So now we know the magnitude of vector B, and we know the direction of vector B. What if you knew the components of A to start with? And we want to know and then we want to calculate what the components of B are. Well, it turns out this is really simple mathematically as well. You just sort of take all the components of vector A, however many there may be, right, 2-dimensional or 3-dimensional, and you just multiply through by the scalar C, everything that the scalar C is. So keep the minus sign on it if there is one, keep all the units on it. So sort of spelled out, what does that look like? If A is written out in ordered pair notation like this, then we would take C and we would multiply it in against each of the components of the ordered pair. If A is written out in ijk hat or xyz hat notation, then same thing. You multiply C, you distributive property. You multiply C against every one of those coefficients of each of those unit vectors. And that's it. And that's it. And you're done. Now, just briefly before we do some more complex numerical examples, let's consider a couple of really common cases. So a couple of really common cases are, what if we have a coefficient, a scalar, pardon me, that is bigger than 1? If we're multiplying by a scalar that's bigger than 1, then what that's going to do is the resulting vector B will be quote unquote stretched and longer than vector A. Now, again, if the scalar has units, has some sort of units like kilograms or 1 over seconds, for example, then B will of course be a totally different animal than A. If A is a displacement, B might be a velocity. So it doesn't really make any sense for us to say something like this. However, if the scalar is a pure number,
So consider for this whole page here, consider whether if the scalar is a pure number. Then what we'll find, then that means if A is a velocity, B will also be a velocity. And what we'll find is that B will then be stretched longer than A if the pure number has an absolute value that's bigger than 1. So here's an example over here on the right. If we multiply A by 2 or 3, then B will be stretched by a factor of 2 or 3 longer than A. They'll both be the same type of vectors, physical quantities, so maybe they're both velocities. If the absolute value of C is less than 1, then of course multiplying A by that scalar is going to end up shrinking A, and the length of B will be shorter than A. So what if we multiply A by a half or 0.3 or anything that is has an absolute value smaller than 1? Then what we'll find is that the length of B will now be shrunken compared to the length of A. Okay? So intuitively, this is a good thing to just understand. And when you multiply a vector by a value bigger than 1, you're stretching the vector. And if you multiply by a value smaller than 1, you're shrinking the vector. What if you multiply by negative 1? Okay, multiplying a vector by 1 would not change the length at all because it's exactly in between these two cases. But then multiplying by negative 1 will flip its direction. You've taken all the components and you've made them all the opposite sign that they used to have. So it's the same thing as flipping the direction by 180 degrees. So you can think of it as adding or subtracting 180 degrees. Doesn't matter, either one. Multiplying by negative 2 would both flip the direction and stretch the length. Multiplying by negative 0.5 would both flip the direction and shrink the length, both. Finally, the sort of trivial case of multiplying by 0, it happens once in a while. And what it does is the resulting vector that you're going to get afterward has no length at all. It has a length of 0. So one of the things that does is it eliminates direction. So it has no direction anymore because notice there's no arrowhead on it. So it's not pointing in any one direction. Units at this point are kind of optional. You'll notice that I often omit units when the value of something is 0. Algebraically, it doesn't matter, right? Because it has 0 length. And we draw, if you're going to draw it, we don't draw any length of the vector at all. It's just a singular point. That's all. So we just draw a point, maybe, if at all. Okay, let's do a couple of examples here with scalar multiplication. So suppose that we have a displacement vector that has a magnitude of 44 meters and a direction of 120 degrees. So if I were to sort of consider this case, let's see here. So 120 degrees is up in the second quadrant. So I can make myself some axes here, and I'm going to consider a vector that points up to the upper left at about 120 degrees. So again, I want to go, if this is the positive x direction, and that's the positive y direction, I'm going to go 120 degrees, trigonometric angle, and at that angle, I'm going to create my vector here. Okay. Okay, so that's just a rough sketch. Okay, it's useful for us in this case to sort of have a rough idea of what's going on. So that's my vector d. Now, what if we want to multiply d by a pure number? So notice this scalar here has no units on it, right? So this is an example of multiplying by a pure number. We can multiply it by a pure number 0.25. What is that going to do to the vector now? Okay. Is it going to stretch it, shrink it, flip it? Well, it won't flip because the pure scalar is positive, so it'll point in the same direction. So the new direction of the result is going to be 120 degrees, and it will shrink it. So it's going to make it 0.25 as long as the old vector used to be. So if I were to write this out as, say, the new vector, let's call the new vector A. New vector A is equal to 0.25 times the old vector D. Then I could say the magnitude of A, and I'm going to write magnitude here just to be really clear. The magnitude of A is equal to absolute value of 0.25 times the magnitude of D. So these are both magnitudes. Okay? and that's 0.25 times 44 meters, and that turns out to be 11. So I want to draw a vector here that is only 11 meters long compared to the former 44 meters. So this is going to be vector A. What if instead we define a different vector here, and let's call this new vector B, and vector B is equal to negative 10 times the old vector D. So the old vector D still looks exactly the same. It's still over here just the way it was before. Okay, well, first of all, let's calculate what the magnitude is. The magnitude of vector B is going to be equal to the absolute value of negative 10. And the only reason I have that decimal point on there is to tell us, well, let's keep 2 sig figs on all these values, times the magnitude of D. So that's equal to absolute value of negative 10 times 44 meters. And that's equal to 440 meters. So that's the magnitude of vector B. How about the direction? Notice that negative 10 is negative, so therefore we need to reverse the direction from D. So if vector D was at 120 degrees, then we're going to say that the direction of vector B is going to be equal to the direction of vector D, either plus 180 or minus 180. So we have a choice. So that's equal to 120 plus 180 or 120 minus 180. Either way, it's exactly equivalent because these are 360 degrees apart from each other. So that's 300 degrees or negative 60 degrees. So these are exactly the same direction. So it looks like the answer here is A. Oh, and what would it look like on the sketch? Well, it would be in the opposite direction from the original vector D, but it would go way off the side of my screen. It would go far off the screen because D, remember, is 44 meters long, and we want to draw a vector here that's 440 meters long. So it needs to go far beyond the screen. All right, I'll leave part C and D to you as an exercise. And the solutions are already posted, so you can try those and compare to the answers. Let's take a look at 2a. 2a is scalar multiplication by a value that has units, a scalar that has units on it. So notice that we're going to take the vector v, which is a velocity vector. We're given the magnitude and we're given the direction. And this time we're going to multiply it by a scalar 1 over 6 seconds, okay? All right, so in this case, I won't bother to draw a sketch at this moment, but let's just go ahead with the same exercise as we did before and calculate. Suppose let's call let's call the result A. So suppose that vector A is equal to 1 over 6 seconds times vector V. So first we want to find the magnitude of A. So the magnitude of A is going to be equal to the absolute value of 1 over 6 seconds times the magnitude of V. So that's 1 over 6 seconds, absolute value, times 25 meters per second. I have to carry all my units, and then the answer to this, therefore, is it's 4.167, so it's about 4.17 meters per second squared. So rounding to, let's say, 3 sig figs, 4.17 meters per second squared. So that's the magnitude of A. How about the direction? Well, ask yourself, are we multiplying by positive or a negative scalar? 1 over 6 seconds is positive. So therefore, the direction is unchanged. Put more mathematically, we could say that the direction of vector A is equal to the direction of vector V. And since vector V was at negative 45 degrees, so will vector A. All right, notice how we carried along the units, just like we would in a regular algebra expression. Okay, so when we multiplied by 1/6 seconds, then we multiplied those seconds through. So meters per second times 1/seconds became meter per second squared. And what that did was it took a velocity vector and it turned it into an acceleration vector, right? See, the units of the new vector are acceleration. By the way, if I wanted to write this out in full vector notation, then I could say vector A. If I put the hat on top, that means I'm about to write the full vector. That's going to be equal to 4.17 meters per second squared at -45 degrees. So that's the full vector, magnitude and direction, or all of the components. That's how we write the full vector. Okay. All right, I'll leave part B to you as an example. And let's just do a couple more. We've been doing 2 examples that have magnitude and direction. So let's do an example now, 2 more examples that use components. Okay, so now suppose that we start off with a new position vector, capital R, where we know this position vector in terms of its components. Now I'm going to, just to give you practice with different types of notation. Oh, I'm sorry. This is a graphical mistake right here. That must be a leftover from the previous slide. Okay, this is just to give you a little practice with different types of notation: I hat, J hat, X hat, Y hat, or ordered pair. My personal preference when I'm just working a problem on my own, and you'll see this in a lot of my solutions, is to use ordered pair notation. That's going to be my default usually going forward. But you're welcome to use any of these notations, and they are all in wide use in different textbooks and different resources. So suppose that we know it looks like a position vector, and we know the x components and the y components. Those are 5.8 kilometers and -3.4 kilometers. Notice the minus sign is hard to spot here because it's just sitting out in front of that 3.4, but we have to mentally attach it to the 3.4. Okay. All right. How do we do scalar multiplication now? Well, now scalar multiplication, when you know the components of something. So suppose, let's call this vector vector c. Vector c is equal to 0.25 times r. Okay, now 0.25, it has no units, it's dimensionless, that's fine. We're now going to multiply it through. So 0.25 times, we have 5.8 kilometers, I hat, minus 3.4 kilometers, j hat. Okay, now we're just going to use the distributive property and multiply this through. So that first term becomes 0.25 times 5.8 minus 0.25 times negative, well, the minus sign is still there, 3.4 kilometers j hat. Now it looks like we're taking a position vector, and we're going to generate a new position vector. So this isn't too different, right? It's 1.455 kilometers times I hat minus 0.855 kilometers times j hat. All right, so vector c is a new position vector. Right, and looks like that answer choice C is the correct answer. Or rounding to 2.6. Let's do the same thing for vector D down here at the bottom. I'll just change color. Vector D is equal to -10 times vector R. So again, just multiplying through, -10 times 5.8 kilometers I hat minus 3.4 kilometers j hat. So that means vector D is going to be equal to -58 kilometers. Oops, pardon me. It's -58 kilometers I hat plus 34 kilometers j hat. Interesting. So vector D is 10 times longer, and it's reversed. Okay, because both the x component and the y component their signs have now flipped. So that answer looks like answer choice D. I'll leave parts C and D for you as extra practice. And finally, let's do one last example with component notation, but multiplying through by a scalar that has some units. And that is 4a. So suppose that we start with an acceleration vector, and we're told what this acceleration vector is in component notation. Okay, so there's an x and a y component. Looks like it's a two-dimensional vector. Suppose that we want to find a new vector which is equal to with the acceleration vector times this mass. So we're multiplying by a scalar, which is a mass, and we're going to find a new vector as a result. Let's call that new vector f. And the reason I'm going to do that is because when you multiply an acceleration by a mass, then you get a force. And we'll learn that coming up in chapter 4. So let's call vector f this scalar, 5 kilograms times the acceleration vector. Now it's the same thing. We have a scalar, and we're going to multiply it through. We know vector A in ordered pair notation. So I'm just going to multiply through just like a distributive property in regular arithmetic. 5 kilograms times 0 is 0, and 5 kilograms times 1.8 becomes positive 9.0. And now we got to keep all the units. I now have kilograms times meters per second squared. All right. Now there are a lot of other correct ways to write this. Notice that all the answer choices are written in I hat j hat notation. So how would you write this in I hat j hat notation? Let me give you a second to think about that. Press pause if you'd like to think about it for a moment. Okay, the way we would write this in I hat j hat notation is we would write the x component times I hat plus the y component with all the units attached times j hat. And if we had a z component, we would do that for the k hat term, which we don't. Now, when a component is 0, like it is here, the custom is not to write that term at all. So we would just say that the vector f, full vector notation now, vector f written with all of its components, is just 9 kilogram meters per second squared times j hat. And that's it. That is the full vector notation. What this is telling us is that the vector f lies 100% along the positive j direction, which we also know as the positive y direction. And there is no component of the vector f that lies along the x direction, right? Notice how there is no I hat term. So the answer here is E. Okay, I'll leave number 4b as an example, as a one for you to try on your own. And now let's talk about vector arithmetic. I'm sorry, vector addition and subtraction, which is the other half of our topic on vector arithmetic. So first, let's discuss what we mean when we talk about addition of two vectors. When we're adding two vectors together, then what we're really doing is if we sort of step through these sort of steps of the graphical method right here, what we're really doing is we're starting with vector A. Right? If I want to add vector B to vector A, so A plus B, we're starting with vector A. And then we think of the tail of vector A as being the start of vector A, and the tip or head of vector A as being the end of vector A. So it's like, imagine traveling along vector A. Now, vector A may not be an actual displacement vector. It could be a velocity vector or force or something else. But still, we often treat these vectors as sort of spatial objects. So you can still imagine starting at the tail of vector A and then traveling along the length of vector A until you get to the end, right? In this case, it's the tip of vector A. When you do that, then notice, then what we're going to do is then we're going to immediately start traveling along vector B. So we can pick up vector B wherever it is in space, move it as long as we don't stretch it or rotate it. Remember that from last time. So it's the magnitude and the direction that define a vector, but not their location in space. We're going to pick up vector B and put it at the end of vector A. in a method that we usually call tip to tail, like this. And then we can think of then going along vector B from its start until we get to its end. And if we had vector C and vector D, then we would continue to do that, sort of tip to tail, as many times as necessary until we've added all of our vectors together. When you're all done, that is your final sort of destination. That's your final location. Now, how do you then draw the so-called resultant or sum? Well, the way you draw the resultant or sum or net vector then when you're all done is you consider, all right, if I had started at the beginning of the first vector of my addition and just gone directly, sort of like as the crow flies, what if I gone directly to the end of the last vector of my addition? So this could be at the end of adding 2 vectors or the end of adding like 50 vectors. What would be the shortest path in space to go from the start of the first vector to the end of the last vector? That is what we're going to call our sum or total or net or resultant. So a lot of times you'll see capital R used because resultant is just a synonym for sum in this case. Okay, that's the resultant vector. Now again, we're talking about these a lot like they're displacements or positions, but these could be velocities, for example, or forces. But it all works the same way mathematically. So that is nicknamed the graphical method for vector addition because what did we do? We just drew a sketch. And if you were to draw the sketch super precisely with protractors and rulers, everything to scale, you could actually literally take out a ruler and a protractor and measure the angle of vector r and the length of vector r, which would give you the magnitude. And you could measure it right off your page, and it would actually be pretty good. However, we're not going to ever ask you to do that for any of our problems because we're going to use more precise mathematical methods that will give us more, well, exact quantitative answers. And that's coming up in a couple of slides after we talk about a little more about the theory. Now, I want you to always keep this graphical method in the back of your mind whenever you are adding 2 or more vectors together. Even if you don't physically draw a sketch, although I will usually recommend that you draw a sketch, especially if you only have 2 vectors, right? Sometimes the sketch can get pretty complicated if you have like 5 vectors. So you can avoid it in that case, especially, well, I'll mention that again later when we get to the component method. But always remember in the back of your mind what you're doing, what vector addition is. It's laying all the vectors down in space without stretching and rotating them, tip to tail to each other, and then when all is done, when all is said and done, you're drawing sort of a new vector that starts at the beginning of the first vector and goes directly to the end of the last vector. So you're shortcutting everything as the crow flies. That is the vector sum. That is what vector addition is. So always keep that in the back of your mind. Finally, before we leave this slide, it's worth noting that as with addition for regular numbers, vector addition is commutative, meaning you can change the order of operation and you still get the same answer. And this is true whether you have 2 vectors or many. So you can prove this to yourself in a number of ways, but if you simply start with vector B, traverse it from its beginning to its end, and then at that point, lay down vector A, like this. So we pick up vector A and lay it down so it's tip to tail with vector B. And then at the end of that, see what our resultant is. Go from the start of vector B to the end of vector A, and lo and behold, the resultant is exactly the same as if we took vector A first and then added vector B. Same direction and same magnitude. So in both of these cases, the resultant R is precisely the same. So vector addition is, as we say, commutative. You can add your vectors in any order that makes it easiest for you mathematically or conceptually. Let's briefly talk about the very simple case of vector addition. If you have vectors that are all exactly parallel, or if you want to talk about opposite directions, we can call that anti-parallel. Okay. So here are 2 vectors that are exactly parallel. Here are 2 vectors that are anti-parallel. They're simply offset from each other right here just for clarity of the diagram. Okay, but again, it doesn't matter if you translate a vector in space, okay, as long as you don't rotate it or stretch it. All right. in that case, notice how if we want to add vectors A and B together, we arrange them tip to tail. So here's vector A, and then at the very end of vector A, that's where we start vector B, and there's vector B. And then how do we get the sum? Again, the sum is if you think about the start of the first vector and go directly to the end of the last vector. So that is the resultant vector right there. Okay. I will usually draw my resultant vectors in a different color or with a very heavy line because that's what I usually care about. It's usually very important to me. Or some books will use a dash line, but I tend not to use a dash line because that looks too much like a vector component. But something to distinguish the sum or resultant vector from all of the other vectors in your diagram is a good idea. If you have two vectors that are opposite to each other, same thing. And here is vector A, start to finish. And then there is vector B, picking up exactly at the end of vector A, starting at the end of vector A, and then finishing here. And now, what do? We go as the crow flies from the start of vector A to the end of vector B. And that's our resultant. So notice that's the resultant vector R right there. All right. This is just like a flattened triangle. If you want to compare this to the triangles we drew in the previous slide, right? Imagine if vector A and vector B were exactly parallel to each other, so they're collinear. Then what would happen? This triangle here would basically just collapse flat, and you would just have vector A plus vector B, and then the resultant alongside. So that's exactly what these are. These are just really flat triangles. That's all these are. Now, what if we have more than two vectors? This is just briefly building on what I said a couple slides ago, and that is you just keep arranging them all tip to tail, tip to tail, tip to tail as needed, D, E, F, however many vectors you may have. And then finally, when you're all done, you go to the start of the first vector and draw as the crow flies vector directly to the end of the last one. So you go from the start of vector A to the very end of vector C, and that's your resultant or sum. And what's remarkable is if you change the order of the vectors. So here we have vector A plus vector B plus vector C. What if we change the order and did B plus A plus C? Check this out. The resultant has the same magnitude and direction in both of those cases. And you could do the other 4 permutations and you would keep getting the same answer over and over again. So it doesn't matter, the addition is commutative for multiple vectors as well. Finally, let's think briefly about subtraction. So the best way to think about subtraction, A minus B, is to remember that that's equal to A plus the negative of B. That is really the best way to think about it. And that's the way our textbook recommends as well. So if you look at these little diagrams over here on the right, remember that A minus B is just equal to A plus negative B. So if you're going to draw a tip to tail diagram, a graphical diagram, what you should do is you start by drawing vector A, and then you add to the end of vector A the reverse of vector B. In other words, the flips of vector B. So this was the original vector B right here. This is -1 times vector B. Notice how it has the same length, but it's just flipped around 180 degrees. Then you would draw, after you add in negative B, maybe add in negative C, negative D, whatever you need. Then your last step is to draw the new resultant vector by starting at the start of the first vector, which in this case is A, and then as the crow flies, drawing a final vector right to the end of the final vector, which in this case is negative B. And that's your resultant right there. If you were to do this same exercise with B minus A, what you would quickly find is you get the negative of A minus B. In other words, if we go up here to the definitions of B and A, notice how B points to the lower left and it's about yay long, and negative A would point to the right and it's about that long. And then we draw our resultant, and the resultant would go from, I'm sorry, B minus A, that's B minus A. The resultant goes from the start of the first vector to the end of the last vector. So our resultant would look like this. So in this case, the resultant has the same length and as it did in the previous case of a minus b, but the direction is precisely reversed. So, and there's other ways to prove this as well with components and everything. What we get is that a minus b, b minus a is exactly the negative of a minus b. And turns out this is exactly what happens with regular numbers as well. If you ask the question, you know, 7 minus 3 is equal to 4, well, what's 3 minus 7? Well, you get negative 4. So it works the same way. There are other tricks that people have for subtracting vectors like a minus b. They draw a parallelogram with the vectors, then take one of the diagonals of the parallelogram, or they put the vectors tip to tip or tail to tail. There's a number of different methods like that, but I have found that none of them is reliably easy to remember. So my strong recommendation is that you simply treat subtraction as adding the negative of the second vector. And we all remember how to do vector addition because that's very intuitive and it makes a lot of sense. Now, the last two slides here on theory, before we do some more numerical examples, address this question that came up a little bit earlier. And that is, the graphical method is all well and good for making a visual sketch to visualize what's happening. But how do we get an actual numerically quantitative exact result, right? Using a ruler and protractor can, it all depends on how careful you are. But what we'd like to do is be able to use mathematics to get, an exact result. Well, there are sort of two main methods for doing this. The first is on this slide, and it's the triangle method, also known as the geometric method or the trigonometric method. It goes by all those names. I'll call it the triangle method for now. And what I'm going to do is well, just to jump down here to the bottom, I'm going to sort of spoil it a little and say this works best when you're adding either two vectors together, or if you're summing three vectors, but the sum of all three is exactly 0. Okay, so I don't have a sketch of that here. But point is, in either of those two cases, you're going to wind up with a nice triangle. The only other time this is good for adding 3 vectors or 4 vectors or more is if the vectors they form extremely symmetrical figures. So maybe if you're adding 3 vectors and a sum and a resultant, or 4 vectors that add to 0 or something, if they fall into exactly a rectangle, for example, then this method is very simple. But those are the times when the triangle method is really the most useful. If you have a really odd scalene triangle like this one that's drawn here, the triangle method can still be used bit by bit, adding 2 of the vectors at a time and finding their resultant, and then adding another vector to that resultant and finding the new resultant, sort of step by step, piecewise. But it's a lot of work because every time you have a non-right triangle like the one shown here, you end up having to use the full law of sines or the full law of cosines and a bunch of other tricky geometry. And it becomes a lot of math. Now, I know this is all of you have all learned the law of sines and cosines from trigonometry class, but this is definitely a much more convenient method when the vectors that you're adding happen to nicely form a right triangle. And in that particular case, then we can use Pythagorean theorem and SOHCAHTOA, and that is just much faster. So when you have a nice right triangle formed by your vectors, then this method is often quicker and easier than trying to write out everything in terms of components. But when the triangles get complicated, like the one shown down here at lower right, the triangle method can be the more laborious path. And the component method, which we'll see on the next slide, is a lot faster and easier. So just to summarize the triangle method, visualize your vector addition. And if you don't have a graphical sketch of it, create one. So there's the vector addition. It's the same one as we had a couple slides ago. So here's vector A, adding, and then at the end of vector A, we draw vector B. And then the resultant is the sort of as the crow flies directly from the start of vector A to the end of vector B. Now, Step 2, redraw that as a sort of reduced or primitive geometric figure. So what we're going to do is we're going to say, all right, this is a triangle. This can be represented as a triangle where the length of the upper side we're going to call b, the length of this, and we may know the value of b, right? We should know the value of b. So we know the magnitude of b. The length of this left-hand side is the magnitude of a. And then we usually know enough about vectors a and b to be able to figure out at least one of these other interior angles. So for example, if we know the direction of a, and if we know the direction of b, in this case, the direction of b is exactly to the right, horizontal, we should be able to figure out at least one of these interior angles right here. Notice it looks to me like if this is the direction of a, theta a down here, then that is also theta a, which means this interior angle here, phi, is equal to 180 minus the direction of vector a. Good. So we know three of the things about this triangle. We know the magnitude of b, the magnitude of a, and the size of this angle phi. What that means is we're now ready, right? We know from the laws of geometry that if you know two sides and one angle, you can figure out the other side and the remaining two angles. So we can use law of cosines to figure out the length of side r, or we can use law of sines after that to figure out either alpha or beta as we wish. The one we can probably do without alpha, we can just find beta. And then if we wanted to know what is vector r, we've just found the magnitude of vector r using law of cosines, and then we can find the direction of vector r by saying, oh, that's just equal to the direction of vector a minus beta. And beta we can find with the law of sines. Notice everything I just did is sort of customized just for this problem and this specific triangle, in fact. So, I mean, I'm using my toolbox of trig and geometry tricks that we can use, in general for any shape or any trigonometric situation. But the order in which the ones I chose to use and the order in which I chose to use them and the way I applied them was customized just for this one triangle that I'm looking at and the things about this triangle that I decided I wanted to know. I decided I didn't care about alpha, but I would need to get beta because why? Because I want to know the direction of vector r. So that's one of the things that makes this triangle method hard to automate. If you wanted to, say, write a computer program or come up with an algorithm that would automatically calculate resultant vectors for a whole bunch of cases. The next method we're going to learn, the component method, is much easier to automate. Okay, and let's take a look at that now. Suppose that you want to add two or more vectors together. Then probably the most general and powerful method that you could use to do that would be to first write out all of the vectors that you want to add together as components. If you don't already know them in components like this, like the components of vector A, the components of vector B, the components of vector C, and so on, then you might need to calculate what those components are using the formulas from last lecture. Okay. Once you have all of the vectors all written out in their components, then it's very easy to simply collect and add up the like components, so the x components for all of the vectors all at once. So here are the x components of all of the vectors I might be wanting to add together, a, b, c, et cetera, et cetera. And what does that give me? It gives me the x component of my resultant. Then collect and add all of the y components of all of my vectors, and that gives me the y component of my resultant. And the same would be true if I had three-dimensional vectors, and I could get the z component. Why does this work? Because if you think about it, at least in these two-dimensional sketches here with two vectors, then you can see that the result, if you think of our graphical sketch, a plus b equals resultant, notice that the position of the resultant, of the tip of the resultant right here, can be obtained by, for the x position of this, can be obtained by adding the x component of vector A and the x component of vector B. There it is. And the y component of this, same thing. There's the y component of vector A and the y component of vector B. Sometimes one of those components is negative. So notice here's the x component of vector A, and now the x component of vector B actually goes backward. because vector B has a negative x component. See that? As a result, what you're left with is the sum of those two values, a positive and a negative component. It still works. It still works. So that's one of the beautiful things about this method is it's beautifully general. Your components of your vectors can be positive, a mix of positive and negative, and this just piles them all up and gives you the total components of the final resultant. So this lets us add any number of vectors all at the same time, right? 2 to 200. It lets us do so for 3D vectors and not just 2D vectors like we were talking about here. It's very easy to automate, right? In fact, the vectors can be at all types of weird and strange angles, and yet you can grind through and calculate what their components are just using our old formulas for finding those x components and y components. We don't need to create a graphical sketch to know what the sum is going to look like, especially if we're adding a whole bunch of vectors and they're all at strange angles. This method will get us to the answer even if we don't have a sketch to use for a sanity check or at the end. And finally, it's very easy for us to combine this process with scalar multiplication. And by that, I mean, it's very easy for us to say, what if I wanted to take R vector is equal to, let's say 3 times A minus 5 times B plus 10 times C and so on. Then it's very easy for me to just multiply all of my A coefficients by 3 and all of my B coefficients by -5 and so on. And it just makes scalar multiplication, combining scalar multiplication and vector addition and subtraction all one-stop shopping. So this is a more powerful method overall, by far. However, like I said, if you're just adding two vectors only and they lie exactly in a straight line or they make a nice right triangle, then the triangle method is probably conceptually the easiest one to use. And the triangle method has the advantage of dealing with magnitudes and directions. So if that's your final goal to get magnitudes and directions, the triangle method might get you there a little faster. Whereas this method deals with components exclusively. So if you're given magnitudes and directions to start, you got to calculate all the components. At the end, if you want magnitudes and direction at the end for vector A, you got to calculate those as well. Okay? So it depends a little bit on what's given and what you want to find. All right, well, that's the end of all the theory. So what I'm going to finish with now is a couple of examples. First, a couple of really trivial, really simple examples here with problem number 5. So problem number five involves two displacement vectors defined up here, right? Vector A is written in components as 25 meters times I had. Vector B is 14 meters times I had. Okay. So note, vector A points in the positive x direction exactly. It has no y component at all. And B does exactly the same. So these two vectors are parallel. In fact, if I were going to sketch them, it would probably look something like this. Here's vector A, and here's vector B. And if I want to make my sketch a little bit realistic, I need to make sure that A and B are in some sort of a ratio of 25 to 14, right? So something just sort of ballpark like that. What would be the sum of B plus A? All right, well, there's two ways to do it. One is to make a sketch and use the triangle method. And then the other way is to use components. So let's do a sketch and do the triangle method first, right? B plus, oops, I'm sorry, that's a mistake. I wanted to do a part D, which is B minus A. Okay, so first let's start with a sketch. B plus negative A is going to look like what? So I'm going to draw B again. So here's vector B. And then I'm going to draw negative A. So I want to flip it around, but it still preserves the same length. So there's negative A. So now I've drawn B and I've drawn negative A tip to tail with vector B. Okay. Now I want to draw my resultant. My resultant is going to start at the start of the first vector and go directly to the end of the last vector. So my resultant looks like this. As the crow flies, this will be the resultant R. Okay. Now, if this were an actual triangle that wasn't flattened, that wasn't squashed flat, if it were a triangle with some area, then finding the length of R would require some amount of work, right? Maybe law of sines, cosines, Pythagorean, whatever, depending on the shape of the triangle. However, in this particular case, we can pretty much answer the question of the magnitude and direction of R by inspection, meaning just by looking at it. So just by inspection, what's the direction of R? And by inspection is just a fancy term meaning it's obvious enough that we can accurately answer simply by looking at the problem and doing it in our head. So by inspection, R has a direction of exactly to the left, right? Or we could call that 180 degrees if we wanted to give it a trig direction, or to the left. It's fine with me if you say phrases like to the left or straight up, as long as the answer is exact. If vector r was really at 179 degrees or 178 degrees and you said to the left, that would be incorrect. Okay? But in this particular case, a and b are both exactly to the right. So when we do b minus a, we do get an answer that is precisely to the left. What about the magnitude? The magnitude of vector r, we can just see by inspection that it's going to be equal to 25 meters minus 14 meters, or 10 or 11 meters. Okay? So we've actually answered the question just by inspection. If we wanted to be a little more formal, this is sort of overkill, but if we wanted to do it by sort of a component method, we can say, okay, components. First, we write our vector arithmetic expression in full vector notation. So full vector r is equal to full vector b minus full vector a. Okay, now we can write these in their components. I'll stick with the I hat notation because that's what we already have. 14 meters times I hat minus 25 meters. I'm just going to use lots of extra parentheses here to keep things extra clear. Okay, and then what that tells me is the answer is negative 11 meters times I hat. So that's also the same vector, r. Notice that this is exactly the same vector. 11 meters to the left is precisely the same vector as negative 11 meters times I hat. Because negative I hat is the negative x direction or to the left. So this is the same exact answer, just written in magnitude and direction notation versus component notation, one of the component notations. If you wanted to write this in ordered pair notation, I would write something like negative 11 meters for the x component and then 0 for the y component. What's the x component of r? It's negative 11 meters. What's the y component of r? It'd be the coefficient multiplied by j hat, which is 0. What's the magnitude of r? It's well, by inspection, you could see it's just 11 meters long. So we know the answer is just going to be 11 meters. If you want to be really formal, you'd say that it's rx squared plus ry squared square root, and that gives you 11. So there's a lot of times we don't need to be quite so formal and do a full derivation of something that's as simple as to the left, or something as simple as what is basically addition and subtraction right here. Okay, let's do one more, a little faster perhaps, from this same problem, and that is part E. Now, in this case, all right, unfortunately, oops, I just deleted what A and B look like. So let's remind ourselves what A and B sort of look like to begin with. So once again, we're going to say, okay, A is 25 meters to the right, and B is 14 meters to the right. So, okay, actually, I think I made these, I got to make them a little shorter. Otherwise, we'll run out of space. So let me try this again. Okay. So what I'm going to do is make them quite short. So this is A and B. Okay. What does 3A minus 5B look like if we were to draw a graphical sketch of it and yeah, to represent it graphically and then do sort of a squashed triangle method with it? All right. Well, we want to take 3A. So what does 3A look like? Let's sort of sketch 3 times A, but it's in the same direction because 3 is a positive scalar. And negative 5B. So I want to draw a vector that's 5 times as long as B, but it's going to be in the negative direction. Okay. Now, when I put these tip to tail to actually show the vector addition, so graphical, although I'm not going to actually measure it with a ruler here. Okay, then we have 3A. We have 3A minus 5B. And I can't tell just by eyeballing it whether minus 5B is going to be longer than 3A or shorter than 3A. So I can guess. I can just sort of guess right now. Right now I'm going to guess wrong, and I'm going to pretend that it's a little bit longer than 3A. And we'll see what happens once we actually do the subtraction. Okay. So let's find out what the lengths of these are. 3 times the magnitude of A is 25 meters. So 3 times the magnitude of A is going to have magnitude of 75 meters. B is 14 meters, so therefore 5 times the magnitude of B should have a magnitude of 70 meters. Aha! All right, looks like I made a mistake. So then I would take my eraser out and just fix it. Oops, I didn't mean to erase the whole thing. Okay, there we go. And now what does my resultant look like? I go from the start of the first vector, the start of the 3A vector, to the very end of the negative 5B vector. So it looks exactly like that. Remember, this space between the two vectors here is just for clarity on the page. It doesn't exist. It doesn't actually exist. So 3A is exactly to the right. Negative 5B is exactly to the left. So the resultant here is going to be exactly to the right. So just by inspection, we can confidently say what our answer is, that the answer for A in magnitude and direction form is going to be equal to 5 meters to the right. And this is exactly to the right. Or you can say at 0 degrees. If we wanted to, again, be really explicit about it, we could say component method. The component method, R, is equal to 3A minus 5B. So again, this is the full vector expression. So it's 3 times 25 meters I hat minus 5 times 14 meters I hat, which is positive 75 meters I hat minus 70 meters I hat, which is positive 5 meters I hat. And that's exactly the same answer. Only this is in component notation, and up there that was in magnitude and direction notation. All right, let's now move on to a couple examples with question 6, which are more complicated because the vectors are not going to be parallel to each other. Okay. In fact, oh, I'm sorry. Okay, I have only one example from question 6. Okay, so now there's an important change here that I'll just draw your attention to. These vectors are now perpendicular to each other. So notice that vector B now is in the positive j hat direction. So in other words, that's in the positive y direction. So I'm going to switch to using a camera instead, so I don't have to use my stylus here. And I think it'll be more. I think it'll be a little more clear and a little more efficient. Okay, just one moment. Okay. So we're going to focus here. You can ignore part B over part F over here to the right. I'll leave that for you as an example, and instead just focus for now on part E. So first, let me remind you of what the vectors are that we are working with. Okay, so vector A is equal to 25 meters in the positive I hat direction. Vector B, so this is from the start of the problem, from the description of the problem, is 14 meters in the positive J hat direction. So if I were to try to sketch these, just to visualize what these look like, then what would they sort of look like? Vector A would look, well, actually, I want to keep them a little shorter than this, because otherwise I will definitely run out of space on my page. Okay, so vector A would look sort of like this. It's exactly in the positive x direction. Okay, and let's say that that has a magnitude of 25 meters long. And then vector B is exactly in the positive y direction. And I want to draw it of a proportional length because it has a magnitude of 14 meters compared to the length of vector A. Now, what is this problem asking us for us to solve? This problem is asking for us to solve 3a minus 5b. So I want to draw a vector that's going to be 3 times as long as a, and then I want to add to it a vector that is negative 5 times as long as b. So let's try, and I'm just going to generate those vectors up here first. So here's a vector that's 3 times as long as a. And we, by the way, we can just tell by inspection that that's going to be 75 meters long. But it still points in the same direction, which is to the right. And then here's a vector that's going to be 5 times as long as b, but in the negative 5 direction. So this is negative 5b. And we can tell by inspection that's going to be 70 meters long. And notice how it's in the negative direction now. Okay. So now I'm going to add those two vectors together graphically. So let's find out what the resultant looks like. So the resultant is going to be equal to 3a minus 5b. So tip to tail, 3a looks like this. And then tip to tail at the end of 3a, I add 5b, which is going to look like that. Okay. Now, I think I've drawn these pretty well to scale. We know that 3a is 75 units long compared to negative 5b, which is 70 units long. So that looks pretty good. Okay. So yeah, I'll just remind myself, this is 75 meters, this is 70 meters, good. And this is exactly a right angle because we know that A and 3A are exactly in the positive x direction, and B, well, negative 5B is exactly in the negative y direction. So they're exactly along the axes. So we know this is precisely 90 here. It doesn't just look like 90. Now I can draw my resultant. My resultant is going to be from the start of the first vector, 3a, to the end of the last vector, negative 5b, exactly as the crow flies. Boom, like that. Put the vector arrowhead on the end, just to remind me which direction it points, right? And it doesn't point the other direction. It's going to point this way because it's from the start of the first vector to the end of the last vector. Okay. All right. Now our goal here now is to try and find what are the components of R, and or what is the magnitude and direction of R. So there's a couple of ways to approach this. We could use the triangle method, or we can use the component method. So let's use the triangle method first. The triangle method says, all right, take this vector addition sketch that we've drawn and abstract it into a sort of primitive geometric shape. Okay, so I'm just going to redraw it, but I'm going to redraw it without the arrowheads. I'm going to say, okay, this side here is the 3A side. We know that its length is 75 meters. That side is 70 meters. We know this is a right angle exactly. I'm going to call this unknown side here length r, okay, which is the magnitude of our vector r. Great. And what is the direction of r? Where does the direction of r live on this diagram over here, right? Well, I can see that this is sort of the negative direction of r, isn't it? That's the negative trig angle. Or I could think of this as being the positive trig angle, right? Well, what that tells me is if I find this angle up here, alpha, then I know that that angle is exactly the trig angle of r, except for a minus sign. Another option I could have would be to find this angle, the other angle, beta, but that's not as useful to me because that doesn't give me the trig direction of r. So if my goal is to get the magnitude in trig direction, alpha is definitely the faster route. So I'll just ignore beta for now. All right. All right, well, I have a triangle. I know 2 of the sides and 1 of the angles. Therefore, I can find any of the other sides and angles that I want. So in whatever order we want to proceed, let's find the magnitude first. The magnitude of r I can get from these 2 sides. So now there's no one approach now. I need to reach into my toolbox of geometry, of geometric formulas and trig formulas, and try and decide which of those tools in my toolbox is going to allow me to most quickly get the length of this side, and then after that, the angle that I desire. Okay, so in other words, solve for the desired unknowns. And I've decided that Pythagorean theorem is going to be one of the fastest ways to go here. So this is going to be equal to, I haven't named these 2 sides with variable names, which I normally do, but I haven't done that here. That's fine. This is going to be equal to 75 meters squared plus 70 meters squared. Okay, now notice this technically, when these were vectors, that might have been a negative, considered a negative component, but we've abstracted this from vector land and we've just made a pure geometric figure with it. And in geometry class, all of the sides of any geometric figures have positive lengths, right? So that's what we're doing. We're just doing basic geometry here, right? This is no longer on the unit circle or anything even necessarily, right? Or on axes. Okay, so when I calculate this, my calculator tells me the answer is about 102.6 meters or about 103 meters. So that's the magnitude of that resultant. How about that angle up in the corner? Okay, I have a lot of choices. I can find that angle, this is a right triangle, so I can find that angle with any of SO, CA, TOA because I now know all 3 of these sides. I know that this is 102.6 meters on this side. So I think I'll use tangent because it uses values that we would have known from the start. But any sine or cosine are also perfectly valid at this point. So tangent is equal to opposite over adjacent. So therefore, alpha is equal to the inverse tangent of 70 meters over 75 meters. Notice that the units now cancel, which is good because we want to give tangent a dimensionless argument, inverse tangent, pardon me, a dimensionless argument. And then we'll get an angle out. So I asked my calculator, what's the inverse tangent of 0.933? My calculator says the answer is 43.0 degrees. Right? Now, I also know that there's another value, there's another answer that is 180 degrees away, which is 223.03 degrees. But I can just see by inspection that this angle here is clearly an acute angle, and it's not it's something on the order of 40 degrees, not 223 degrees. So I'll just discard that. Okay, now I'm almost done. Remember how we already decided earlier that alpha is equal to the negative of the trig direction that we want, or put another way, the trig direction we want is actually the negative of this angle right here. So therefore, the trig direction of R is going to be equal to negative 43. Right? Or if I wanted to, I could also add 360 degrees to that. And that would be 317 degrees, which also points in this same direction. This is also 317 degrees down here. So those are both correct answers for the trigonometric direction of R. What if instead of this, I wanted to use the component method? Well, that would also work. And I'll just show it to you for completeness, but we already have our answer for, as far as magnitude and direction. Okay. What if R, we start again with our main equation here, writing this out as full vectors. R is equal to 3 times vector A plus negative 5 times vector B. So I know what vector A and vector B are in components already. So that's equal to 3 times, and I'm going to use lots of extra parentheses now for just for clarity. 3 times 25 meters times I hat, and that's it. That is vector A, minus 5 times 14 meters times j hat. So, yeah, I should stop using the marker. This is equal to 75 meters times I hat minus 70 meters times j hat. Actually, that's it. That is the answer in component notation right there. There is no further simplification to be done. If I wanted, I could write it in ordered pair notation, and it would look like this. Positive 75 for the x component, comma, negative 70 for the y component. And you have a choice. You can either put the units on the outside of the ordered pair, or you can put the units on both of the components. So you have a choice. You could write it as 75 meters, comma, negative 70 meters. And that's equally correct. Okay. Now, if I didn't already know the magnitude and direction from up above, if suppose all I did was given this, how would I then get the magnitude and direction? I would have to remember from the previous lecture how we convert between components and magnitude and direction. So I would say, okay, once I have a vector and I know its two components, then I would say the magnitude is equal to the square root of the x component squared plus y component squared. It looks like a Pythagorean theorem, right? Now remember, the units applies to both of the components, so I'm going to carry it around inside the radical here. And then I ask my calculator what the answer to that is, and it says 102.6 meters. And I look at the problem as a whole, and I say, oh, it looks like about a 3 sig fig problem. So 103 meters. How about the direction? From last lecture, the trig direction of a vector r is going to be equal to the inverse tangent of the y component over the x component. So that's going to be equal to, I'll go ahead and write on the next line. Negative 70 meters is the y component. Positive 75 meters is the x component. Notice how the meters cancels here. And that's equal to inverse tangent of negative 0.933. And my calculator tells me that the answer to that is negative 43.03. And I know, my calculator doesn't tell me the other answer, but I know if I add 180 degrees, I will get the other one. And the other answer is 136.97 degrees. Now, how do I know which one of these is correct? Okay, suppose I don't even have a sketch or a drawing. Well, is there a way for me to figure out which quadrant vector r lies in? When we look up here to vector r? If you're thinking, yeah, look at the plus and minus signs on the two components. You're absolutely correct. So what quadrant am I in if I have a positive x component and a negative y component? I hope you're thinking quadrant 4, and that's exactly what we want, the fourth quadrant, and not the second quadrant. So this is the answer. If I want, I can round and maybe 10 to the 10th degree. Sig figs are strange with angles, so I'm not too picky about those. All right, that's it. We've now found the magnitude direction of vector r, knowing the components. And notice that matches what we got earlier. Okay, that concludes lecture number 9. And so please review the remaining example problems that are on the tutorial sheet that we didn't do if you'd like extra practice, not for credit. And then whenever you're comfortable, then leave the rest of those behind and go and work on the 4 credit problems in Mastering Physics.